This video is about stellar evolution. That's topic 14. And we are following the Edexcel GCSE Astronomy specification. So this is topic 14, and here is what the topic is all about. As usual, I'll show this, but I'm not going to go through it in detail. You can have a look at each part of this if you're interested. We're going to start with the Messier catalogue. Here's Charles Messier, this French comet hunter, and he was looking at different objects in the night sky and kept thinking he was finding comets because that's what he was looking for. So he would then have to have a look through all the different documentation to see if what he had found was indeed a new comet or whether it was something that had already been found and had already been catalogued. At the time, it was confusing because there were lots of different catalogues. So Messier came up with his own catalogue. Now, the catalogue, it started small, it grew, and then ended up including 110 objects. These objects were not planets because they did not appear to move relative to the background stars as planets do. But they weren't stars either, because they weren't single pinpricks of light. There was some blurriness to them, some uncertainty about the edges of them, perhaps. So this is the full Messier catalogue, all on one screen. You've got Messier 83 here, which is a personal favourite of mine, but let's not worry too much about that. There's the Messier catalogue. I mean, you know, there's plenty on there to admire. It's all too small for you to see here, but what a universe we live in. How fantastic. However, there are more than 110 blurry things in the sky that you can see, and the better the telescope you have, the more that you can see. So a better catalogue was needed as we added more and more of these blurry objects. Most of these are galaxies, there's some nebulae in here as well. Some of these are star clusters. We needed a new catalogue. Enter the New General Catalogue, the NGC. Thanks to John Dreyer. He was a Danish astronomer, and he started putting together other catalogues into a new catalogue that included a bit of everything. Well, everything, hopefully. So he started with the catalogue that had been put together by the Herschel family. They were also comet hunters, but they also found a bunch of nebulae and had to write down what they'd found, so they didn't keep finding the same thing. So he started with, it's based on Herschel's catalogues, and he carried on adding to it. So the NGC ended up with 7,840 objects in it, but then he added a bunch of index catalogues, these appendices, these supplementary catalogues, 2 of them, onto the end of it, and in the end he added another 5,386 objects. This is a huge catalogue. So what do you do with the catalogue? Well, if you look through a telescope and you think you've found something that no one's seen before, you need to check. You can't just start writing onto Facebook or Twitter, or it's not called Twitter anymore, is it? X or whatever. Oh, look, I found the new comet. You've got to check first. Now, nowadays, what we do, of course, is we Google it. Other search engines are available. We would look up online catalogues, or you've got some great software by companies like Celestron where you can just look up full catalogues of different bodies. And you can look up bodies based on their right ascension and their declination. And we've talked about what right ascension and declination are in previous videos. It's a way of addressing a location within the sky. So you can do that, and then have a look and see, is there an object already there? What's the description of that object? Does it match what I think that I have seen? So that's how it works nowadays. The way it used to work, of course, was very similar, except it was all done on paper. It was all done with books. And so in this catalogue, you can see you've got your right ascension, declination listed. You've got some information about the apparent magnitude there as well, and some other information about the body. And it's in a logical order. So you'd look up, right, where's the right ascension? Now look down the declinations. Now let's have a look and see what I found. So it was in a logical order. So you can see whether you've discovered something new. Now this moves us nicely on to the naming of celestial bodies. And by bodies, I don't just mean stars here. I could include nebulae or whole galaxies in this. But we need to name what we can see. So let's talk about stars. And anything that we find that isn't a star, we have to find a new fancy name for it. But it doesn't matter. Let's start with stars. The naming convention we use is called the Bayer system, the Bayer designation system. And here's a star map looking at the sky. This star map is centered right here. Hopefully you can see what this star right in the middle is. If you can't see, then have a look at the coordinates for it. That might give it away. That is Polaris right there. And this is the northern hemisphere. You can see down here Ursa Major with our plough, which the Americans might call the Big Dipper. Down here, you've got my favourite up here, Cassiopeia. You've got Cygnus over here. And things like Cygnus, Cassiopeia, Ursa Major, very recognisable in the night sky. You get really good at spotting these things. Anyway, let's get back onto the topic. The designation. The sky is carved up into these different regions, these different areas that we can see. We call them constellations. Con, with, collected, grouped together, and stella, star. So constellation does just mean grouped together stars. And they're only grouped as we see them. We're not saying these stars are actually near each other. They just appear to be near each other. So here we've got our constellations, and within each constellation there is going to be one particular star which is the brightest, then one that's the second brightest, then one that's the third brightest, and so on. And so we name our stars. We start with the brightest one and we call it Alpha. So the Alpha star is the brightest one in a particular constellation. Then we have the Beta star, then the Gamma star, and so on and so on and so on. However, that rather limits us on the number of stars. So the Bayer system is extended beyond this list, and you do need to learn these Greek letters. You need to be able to recognize what these Greek letters are, so you know the order of them, so you know what's brighter than what else. Now, I'd be very surprised in a GCSE if you end up down in the dark depths of this side of the Greek alphabet. You're probably going to be sitting near the top, but still, alpha, beta, gamma, delta, epsilon, zeta, eta, you know, that sort of thing, that order is worth memorizing. So the the Bayer system, the Bayer designation system, it has to include more, because there are more than 24 stars in a constellation, but there are only 24 Greek letters in the Greek alphabet. And even then we can't use all of those letters. So what do? So on this Bayer system, we need to add more letters on. So we've added Roman letters to the end of the Greek letters. So you see here we've got alpha, beta, gamma, delta, epsilon, zeta, eta, theta, and so on and so on and so on. You get to the end of the Greek alphabet with omega. That's the final letter. They don't have Z. Well, they have zeta, but that's all the way up here somewhere. And then we start A, B, C, D, E, F, G, H, I, and so on. I say and so on because we need to do some tweaks. We don't use a lowercase a because it looks too similar to an alpha. And we don't include J because it looks too similar to I in handwriting. We don't use V because it looks too similar to the Greek letter nu. There it is. There's nu. N-U. So I can't understand this. We're avoiding letters that look too similar, very sensible, but then we've got O and we've got Omicron. So I don't understand why we've got two letters that are identical in this Bayer system. It's not very well thought out, I have to say. It's also worse than that, because where there are binary stars, well, let's say double stars, which you couldn't resolve with the naked eye, we then had to find a better way, so we started talking about adding stars onto things. So, you know, Sagittarius A star to say it's even brighter, and so on and so on. So there's some funny things we do in the system. It's not a perfect system. So how do we refer to our stars? We refer to them by the name of the constellation, and then by the Greek letter or Roman letter. So there are 88 constellations, but we don't just say Aries, we would say Eritis. We don't say cancer, we say cancri, I think that is. I don't speak Latin, so I'm not wonderful at pronouncing these. So instead of Libra, it's Libre. Apparently, this is the possessive form of these nouns. I'll have to trust someone with that. I'm not an expert in Latin grammar. And you can just look all these up, but you'd recognise them. You see Cap, you know it's to do with Capricorn. You see Aqua, it's to do with Aquarius. Aquil for Aquaries is a bit interesting, so I included that one on this list because I thought that was odd. Leo for Leo, that's an easy one. Lib for Libra, and so on. So most of them are easy to figure out. So we wouldn't write the whole word, we'd just use the abbreviation. Now, we're moving on to a new topic. That's the biosystem. Let's move on to a new topic. The new topic is all to do with what's happening inside stars. So inside stars, you have a plasma. And that plasma consists of protons and electrons. And it will also consist of things like deuterium nuclei, maybe, well, including tritium nuclei, and there could be other nuclei as well, helium-3, helium-4, and so on. But there's a whole soup of these ions like hydrogen ions, which can be just protons, and electrons. And the temperature is so high that the electrons are no longer going to be bound to their atoms. The collisions between the particles are so energetic, the electrons get flung straight out because of the high temperature. So you probably recall, as you increase temperature, you increase the kinetic energy of the particles we've got in our system. Well, when that energy is high enough, the collisions between those particles is energetic enough to knock those electrons out. So that's what we've got going on. So inside stars, nuclear fusion happens. Nuclear fusion is where two protons, for example, can come together and fuse into a new isotope. So in the case of two protons, they'll actually fuse into deuterium. And I suppose we could get two deuteriums and fuse them into helium, and then we've actually created a new element in the process. And I'm going to use the word created, and someone's going to go into the comments section and complain that I've used the word created. Well, come at me, go into the comments. I do love your comments, it's good. I have no problem with using the word created in reference to the fact that there was no helium before and then there was helium afterwards. The word created seems perfectly appropriate for me in that sense. But anyway, let's leave that. So what's going on in nuclear fusion? Protons have the same charge as each other, which means they repel each other. So as you move two protons near each other, they're repelling, they're pushing away from each other, getting harder and harder to get together, because the closer together they are, the greater that repulsive force is. So how do I get them close enough together that I can call it a single particle? Well, it turns out that for protons and for neutrons, there's another force. A force that's included in A-level physics. It doesn't usually get talked about in GCSE physics, although I talk about it with my students, but I don't think, well, it's definitely not on my specification. I don't think it's on the GCSE specifications that I don't teach either. So you've probably never heard of this force before, but it's called the strong nuclear force. So I'm showing you a graph here. And if we just look at this red part here where my cursor is currently tracing, this is showing the electromagnetic force as a function of the range between two protons. So when the two protons are about 2 femtometers apart, that's 2 times 10 to the negative 15 meters apart. That's very, very close together indeed. 2 times 10 to the power of negative 15. Woof. When you've got that, you've actually got a tremendous force of repulsion between these protons. Look, it looks like 0.5-ish, but that's 0.5 times 10 to the power of 4. That's 5,000 newtons. 5,000 newtons of force acting on two protons. Now, to put that into some sort of comparison, some sort of numbers that you understand, my mass is well, it's a little bit more than, but let's say it's 100 kilograms. So if I have a mass of 100 kilograms, my weight is about 1,000 newtons. That's my weight. And I'm made up of an awful lot of protons. And we're talking here about the force between just two protons, just two of them. And they get close enough together, can get more than 5 times my weight in Earth's gravitational field. That is an incredible force. So you've got that repulsive force that increases in magnitude quite significantly as the protons get closer and closer and closer together. But there's another force. If it was only the electromagnetic force, then you'd never be able to get protons to combine into a single particle and would never get nuclear fusion happening. But there's another force, the strong nuclear force. Now, at a reasonable range, about 3 femtometers, the strong nuclear force doesn't act, or at least the range of it is far too short. You don't experience the strong nuclear force at that sort of range. As you bring two protons together, the strong nuclear force gets greater and greater in magnitude. But it's attractive. So if we look around here, about 2.5 femtometers, we've got electromagnetic force up here, which is repulsive, and we've got the strong nuclear force, which is attractive, but it's less magnitude. If you look really closely, you'll see that the blue line is closer to 0 than the red line. 0 on this graph is here, this line going down the middle. The green line shows what I get if I add those two forces together. So let's call repulsive positive, attractive negative. When you add those two numbers together, it's going to make the sum smaller. And so that's why that green line is closer to 0 newtons. And it starts on the repulsive side. So even though the strong nuclear force is acting at around 2.5 femtometers, the electromagnetic repulsive force is still the strongest one. So your protons getting within 2.5 femtometers of each other are still going to be repelling each other. But watch what happens as we get those protons closer and closer together. You get to around here, which on this graph is showing at just below 2 femtometers. Actually, I've doctored some of these numbers to make them a bit easier to see. This depends very heavily on the isotope. So this is an approximation. But you'll notice on this graph, around about there, just below 2 femtometers, all of a sudden the attractive force, the strong nuclear force, is now a greater magnitude than the repulsive force, the electromagnetic force. So those two protons, if they get close enough together, they're no longer repelling each other. They're now attracting each other, pulling each other closer together, even closer together. Now that's interesting. That's something that you don't really notice in the everyday world, because the strong nuclear force is such a short range. But in stars, you see this happening. So the strong nuclear force gets really, really strong. We're talking 2,500. Oh, sorry, this is 25,000 newtons of attractive force. 25,000 newtons acting between two protons, and I only have a weight of 1,000 newtons. It's mind-boggling forces we're talking about. How many protons are in me? Gravity's a really weak force. Anyway, so we've got these two protons. They're now about a femtometer apart. They're really strongly attracting each other, so they're going to keep pulling themselves closer together. But then the strong nuclear force does something. It tricks us. It goes zoop and becomes repulsive. It's the only force that we know that does this, that switches from being attractive to repulsive at different ranges. Now, the reason for that is incredibly technical. It goes way beyond even A-level physics. So I'm not going to go into it now for two reasons. One, we don't have a lot of time and I want to cover the GCSE astronomy stuff. And two, I can't remember it. So whichever of those reasons we think is the most important. Right, so we've got our strong nuclear force becoming repulsive. So what does that mean? Well, that means that as the protons get closer and closer and closer together, eventually they're so close together that now they're actually repelling each other. And as they repel each other, slowing down, stopping, and then start moving apart, if they move apart if they move apart too far, then they're going to attract each other again. Then they're going to repel each other. They're going to attract each other. They're going to repel each other. And so you're going to get these two protons settling down in an equilibrium position where the resultant force is zero. And not only is the resultant force zero there, it's also here. But here, where my cursor is, the resultant force is indeed zero, but if the two protons move slightly further apart, then they repel and they shoot apart. And if the two protons are slightly closer together, then they attract and they come together. So that's what we call an unstable equilibrium. But this equilibrium, where my cursor is now, if the two protons are pushed a little bit further together, they move apart, they get pushed apart. And if I pull the two protons slightly further apart, they get attracted back together again. So that's a stable equilibrium. Now, the two protons aren't going to stay as protons. Actually, one of them is going to decay into a neutron, but we'll talk about that in a second. So here's some notes on this. Hydrogen contains a proton. Protons have the same charge. They repel each other. Forces transfer momentum. I thought that was important to mention. And so as these protons move towards each other, and they've got momentum therefore in opposite directions, this force is going to transfer momentum from one to the other. So in other words, one that's got, let's say, positive momentum, whatever direction that is going to be losing momentum, and the one that's got negative momentum is going to be gaining momentum, but in the positive direction. So the magnitude of the momentum of both protons is going to be reducing. Now that's a mouthful. If you didn't follow that, just go back, rewatch that bit, or read what this text says. Remember, momentum is a vector. This ties very closely with the GCSE of physics and the idea that forces transfer momentum between bodies and that momentum is a vector, so we do have to be a bit careful with it. So anyway, eventually the two protons are going to stop moving, they're going to be sat there, and that'll be fine. So it's going to look a bit like this if there's no strong nuclear force. I'll show you that animation again because I'm very proud of it. Here we go. Or they get closer together. The arrows that are growing show the magnitude of the electromagnetic force of repulsion. Fine. Then, if we have our strong nuclear force, and I've got some notes here about it, that's not what happens. The strong nuclear force, if they come within range of that, then the protons will stay where they were, where they'll stay close together. So I've got some notes here. So the electromagnetic repulsive force is going to stop them getting too close together. We call that the Coulomb barrier. But you can overcome that Coulomb barrier. You can defeat that Coulomb barrier. You can breach that Coulomb barrier if the protons have enough momentum to start with. Because then, as that force takes that momentum away, slowing them down, by the time they stop, if they've got enough momentum to start with, by the time they stop, they are within range of that strong nuclear force that's attractive. You could think about this in terms of energy if you prefer. I chose to do this in terms of momentum and in terms of forces, but you can think about all this in terms of losing kinetic energy as the protons approach each other until they have no kinetic energy. And if they have zero kinetic energy, in other words, they've stopped within range of the strong nuclear force, then actually that's going to pull them closer together still. So you get this. Bonk. We're now close enough together, this force switches on and holds them together. I'll show that animation one more time. Bonk. So they have to be close enough together. I've shown them touching here, but they have to be close enough together for that force, the attractive force, the strong nuclear force, to be acting. Right, but you don't get two protons bound together as a single nucleus. That doesn't happen. What happens next is one of the protons changes. As it says here, it's incredibly unstable to have helium-2. In fact, I'm not convinced we've ever isolated helium-2 and done any sorts of experiments on it because of how short-lived it is, because of how unstable it is. Now, the weak nuclear force, that seems to work to reduce the energy of whatever our system is. So in the system we've got these two protons bound together, that's quite energetic, it's not very energetically favorable. The weak nuclear force can act to make that more stable. And as it says here, it does that by turning protons into neutrons. So this is a fourth force. We've talked about gravity. I weigh 1,000 newtons-ish. That's a gravitational force. And the gravitational force between individual protons is negligible if it acts at all. We don't even know if it actually acts. We haven't managed to test that. Although we have been looking at the effect of gravity on anti-hydrogen only in the last few weeks when I've recorded this video. So maybe gravitational forces, we are now able to measure the effect of gravitational forces on particles that small. I haven't read the paper, so I won't say any more about that, but that's interesting. So we've got the gravitational force, very, very weak. We've got the electrostatic force or electromagnetic force. That's much stronger. As you've heard, it can become very, very strong if the protons are close enough together. You've got the strong nuclear force, which is weird because it becomes attractive at short enough ranges. And now we've got a fourth force, the weak nuclear force. And to our knowledge, those are the only four forces in nature at the time of recording this. There were some papers that were released, I don't know if they were peer-reviewed released, but there were some things released, I think it was last year at some point, saying there's some hints that there may be a fifth force of nature, which is quite exciting. And again, I haven't got into a lot of research on that, so I'm not really going to comment on that at the moment. It'd be nice if there is, though. We always love it when we discover new physics. Physics is one of those odd disciplines where our job is to try to prove ourselves wrong constantly. It's brilliant. That's why when students make mistakes, it's good. It's good to learn from mistakes because that's literally what physicists do for their entire career, is make mistake after mistake and learn from it. And then hopefully contribute something so the next physicists who are making mistakes will continue that glorious path. I mean, how much physics over the years have we corrected because we discovered that mistakes were made? That's our job. Anyway, doesn't matter. Weak nuclear force, a fourth force of nature that turns protons into neutrons. So what does it do? Well, it does this. We have a proton here. Don't worry too much about the OODOO at the moment, just a proton here, which is going to turn into a neutron. Don't worry about the UD. It's going to turn into a neutron. A T here just indicates the arrow of time, if you like. So this proton's going to trundle along like this, and then it's going to emit something called a W boson. That is a particle which carries the weak nuclear force. The W boson here is charged, so it carries away the positive charge, leaving behind, well, the neutron. You've got a proton, you've stripped the positive charge out, it's not a proton anymore, it's now a neutron. Got a yogurt pot, and you take the yogurt out, you've just got a pot left. Anyway, I'm not calling charge yogurt. So anyway, we've got this proton, it emits a W+, and it turns into a neutron. Fine. We can also see I've included UDU. These are the names of the quarks. If you're studying I think it's the Edexcel GCSE physics, or it might be the IGCSE physics. There's a little bit in there about quarks as well, in the higher tier physics stuff. It's not included in the AQA GCSE. It is included in the AQA A-level. So you've got your quarks there. If you don't know what they are, don't worry too much about it. They're particles that make up protons and neutrons. Well, some of them. You're not ready for that yet. So but you will be. Right, so the W boson, the W+, will then decay into two particles. In this case, one of them is going to be a positron, that's an antimatter version of an electron, and a neutrino, that's the Greek letter nu, that's an electron neutrino. Notice that the arrow here is going backwards. That's interesting. This is Feynman's interpretation of antimatter. Feynman interpreted antimatter as being equivalent to matter with a negative time axis. You switch all the quantum numbers, apparently that's the same in the equations as just making time negative, which is interesting. It does mean that these Feynman diagrams are very useful because you can rotate them and you can reflect them and you can do all this sort of stuff and they still work, but only if you make the antimatter arrows point backwards in time. but that is beyond GCSE levels, so let's not go too far. We emit the W boson. The W boson does not last very long at all. It's a very, very short half-life, and so it decays very quickly. And what I'm telling you is a certain amount of fiction, because it's not quite as simple as I'm making it out, but it's good enough for us for now. The W boson decays into this positron, anti-electron, so positron, and this thing called a neutrino, which barely interacts with matter at all. It's got no charge, very little mass. Billions upon billions of them stream through you every day. There's just billions and billions and billions of these things because they're very weakly interact with matter. And these positrons. And that's all going on inside the sun. What that does is it increases the temperature of the material in the sun, which means that those particles bounce around more quickly, which means they're pushing outwards as they do so, because they're more. If you imagine an imaginary membrane at some point in the star, and the particles inside that membrane are colliding with it faster, yes, and more frequently than the particles outside that membrane, that's going to produce an overall force outwards on the membrane. Actually, there's no membrane. We don't need one. It works still with stars in the same way. You've got this sort of layer, a layer of hydrogen, and the deeper you go, the higher the temperature of those layers, and so those layers push outwards effectively. And there are other things going on as well, these outward forces. There's radiation being emitted, infrared radiation, which is going to come outwards from the hottest parts of the star as well. And then there's other particles that are created, and I do mean the word created. Again, if you don't like it, get in the comments and start complaining about me. But the particles that are created, like the W boson, which then decays into the positron, there are other nuclear reactions happening, creating other particles, and they all fly outwards, which means it's going to push the star apart. It's going to try and swell this star out. So that's what I'm talking about here. Now, what about those positrons? What happens to those positrons? Those positrons will annihilate electrons, or with electrons. So it doesn't happen immediately. We always say, look, when matter and antimatter come together, there's annihilation, loads of energy is created. Again, if you don't like them, I'm not going to say it again. Energy is created. That's going to cause a lot of people to be upset me saying that, but I'm going to stand by it. People who know me know that, I don't want to pull rank or anything, but I'm fairly qualified, and I'm going to say energy is created. What are you going to do about it? So, energy is created in this collision, in the collision of positrons and electrons. What you probably don't get told is it's not immediate. The positrons have to be traveling slow enough to interact with the electrons in a way that causes annihilation. So believe it or not, the positrons actually collide and exchange energy as they move through the matter of the star until they're given enough energy up, until they're going slow enough to interact with an electron and annihilate and produce two gamma photons, two blasts of electromagnetic energy in different directions. Electromagnetic radiation. I didn't like calling it electromagnetic energy. That's naff. So that's what's going to be going on. And of course, every one of these collisions is going to exchange energy, increasing the temperature at the core of the star. And then ultimately, we've got radiation being produced as well. So that's interesting. That's also going to increase the temperature. That's also going to increase the outward pressure on the star. Or the outward forces on the star, should I say. I've said here as well that the electromagnetic radiation that's released, it's gamma radiation, will also be absorbed, also increasing the temperature, also increasing the speed of the particles, also increasing that outward force. And now I have to talk about radiation pressure. Now, this is one of those terms that bothers me. I don't like it, but I have to teach it, and you have to know it. I don't like it because of the way the term radiation pressure often gets used. Indeed, it gets used this way by experts in the field who are far more qualified than me. Proper astrophysicists will talk about balancing gravity with radiation pressure. That doesn't make it right. It's just when you get comfortable in your field, you become a little bit more comfortable with using perhaps a little bit of imprecise language, but everyone in your field understands it. I'll give you an example. When we teach electromagnetism, we often talk about current as having a direction. That doesn't make any sense. Current is a scalar. That's just one example. Often people will talk about heavy particles. Heavy meaning high weight. No, we mean they've got a lot of mass, of course. So, we can be a bit lazy with our language, but we have to earn the right to be lazy with our language. And I don't think I've earned that right yet. So that's why this section bugs me a little bit. Anyway, pressure is defined as force divided by area. And if there's this radiation force, or this general outward force caused by difference in temperature and caused by the radiation, which is pushing outwards, and again, imagine that sort of spherical membrane within the star, so it's pushing outwards on that, this imaginary membrane, which has a certain area, then you could correctly calculate what the pressure is due to the radiation and call it radiation pressure. So the term itself isn't the thing I've got a problem with. Pressure, of course, is a scalar, though. It doesn't have a direction. So we took here, it says the last sentence here, air pressure acts equally on all the walls of the container. That is true. Produces an outward force on the container. That is true. Outward force. Not outward pressure. Pressure is a scalar, but force is a vector, and the pressure produces that force. Well, that's not quite true either. Again, I'm limited by the English language. But again, we often say pressure having a direction for convenience, but that doesn't make it right. So, why doesn't the star just go and spread outwards and diffuse out forever and ever? Well, it doesn't because of the force of gravity. There's a force of gravity pulling that matter back together. So the example here, if you've got gas in a bottle, but there's no walls. There's no wall. The star doesn't need this imaginary membrane holding it all together. Gravity does the job perfectly well. In a sense, it's sitting in a gravity well, at the bottom of a little gravity well, and all the matter that tries to escape is going to fall back into that gravity well. That's the bottle that keeps the stars in. Okay? So that is the gravitational force. That very weak force, but because there's so much matter in a star, it becomes more significant. It's not significant on the particle collision scale, but it does become significant on the scales of, planets and stars and things, in this case stars, because of how much mass there is there. So even though it's weak, it becomes important. So we've got this issue that we say that the weight is balanced with the radiation pressure, and that's why the star doesn't collapse. Radiation pressure is high enough and doesn't expand out forever. The weight of the star, well, the matter in the star is high enough. But I'm not keen on that terminology, but that's just a me thing. Here's a lovely diagram showing a bunch of arrows. The arrows pointing out are due to radiation pressure. The arrows pointing in are due to the weight. And here we've got a picture of the star in a gravity well. It's not a great diagram, if I'm honest with you. It's apt to cause misconceptions because what we're looking at here is 2 dimensions of space, and then the third dimension, what maybe here would be vertical, is actually a graph of gravitational potential, which is related to energy. So not a great graphic, but I'm hoping it does enough to show you the idea that stars exist in some sort of gravity well. So one type of star we're going to talk about are the main sequence stars. Main sequence stars are the ones where this outward force, due to nuclear fusion and therefore the higher temperature of the core and the radiation, is balanced with the inward force on the matter, which is caused by the weight of the star. And those 2 forces balance, and so that star can remain the same size for a very long time. In some cases, our star is going to be around for about 10 billion years. I mean, half of that's already gone. So within the star, we'll just talk about within the star. Within the star, there are these different regions. You've got this core, which is incredibly high temperature, millions, tens of millions, hundreds of millions, billions of degrees Celsius, really high temperatures. You've then, as you go outwards, you've got this sort of radiation zone. That's where the energy is being transferred outwards, mainly by radiation, by electromagnetic radiation blasting out from the nuclear reactions in the core. That's transferring the energy through that zone. The convection zone is where the matter is able to cool enough as it moves further away from the core that it can then sink back down. And we get those convection cycles in this convection zone. And maybe we'll talk about the chromosphere and the corona and the photosphere at some later point. So we've got these different layers of the star. Now, the radiation pressure, in big heavy quotes, doesn't always balance the gravitational force. When it does, we've got a nice stable star, sure. But the radiation pressure can decrease. And when the radiation pressure decreases, so the gravitational force becomes higher, that means the star's going to contract down. If it's the other way around, the star's going to expand out. So what would make the radiation pressure decrease? Well, that would be a reduction in the rate of nuclear fusion reactions. And that could happen if we were using up the fuel. That would happen. Now, as the star contracts, or at least the core of the star contracts, that's going to increase the temperature, which is going to mean that more of those ions, more of those protons can get within range of each other to fuse. So as the core of a star contracts, that can actually increase the rate of nuclear fusion, which will increase the temperature and therefore increase the radiation pressure, pushing the layers of the star out. But pushing the layers of the star out will decrease the temperature, which will reduce the temperature, reducing the rate of nuclear fusion, which will therefore reduce the radiation pressure, and the layers of the star can contract back in. As they contract back in, that's going to increase the temperature in the core, which is going to increase the fusion rate, which is going to increase the amount of radiation pressure, which is going, and you see how this is going to work. Now, there are stars that are in a fairly stable, oscillating pattern. And we can talk about them later in this course. We're not going to talk about them right now. But even our sun has a cycle, a little bit more than a decade cycle, where it sometimes is slightly higher radiation, sometimes slightly lower. It's not a very big difference with our sun. It's very stable, and that's a good thing for us. So I don't like the term life cycle, because it's not really a cycle. You've got the star forming. The star stays pretty much the same size for most of its life, if it's a main sequence star, but then it's going to expand. It says here gradual warming as well, but it's going to expand. And as it expands, there's a few different things that can happen depending on the mass of the star. Now, a star like our sun, as it expands, the outer layers are going to puff away. The middle bit, the core, is going to contract right the way down. And eventually, the outer layers that puff away will leave the star altogether, forming a nebula. And the middle bit, that core, is going to cool down and compress and cool down just because it's still radiating energy the whole time. It's glowing because it's so hot. And eventually, we'll have a white dwarf that will cool into a black dwarf. So that's sort of what our star is going to be doing. At the bottom of this slide, I start. You know what I'm like. I like going into good physics. So I started looking at different fusion reactions. So deuterium fusing with deuterium. That's what we're looking at here. Deuterium. The graph that's here is showing what we call binding energy per nucleon versus number of nucleons. So the number of nucleons in hydrogen, in this case, is 2 because it's deuterium, and in this helium is 4. So we're looking at moving from the left of this graph towards the right. And as you do that, you can see that the line goes up. We increase the binding energy per nucleon. What is binding energy? Well, it's not an amount of energy that the thing has. When we say binding energy, it should really be called unbinding energy. It's the amount of energy we'd have to put in to split the thing up. So having more binding energy means it would require more energy to split the nucleus up, which means it's, generally speaking, more stable. So deuterium fusing means it requires more energy to split the helium up. If you need to put more energy to split it up, that means when you formed it, more energy came out, because energy is in this lovely, well, energy and mass is in this lovely balancing act. Maybe I shouldn't go into that into too much detail at this stage. So deuterium can fuse at around about 1,000,000 Kelvin, which to 3 significant figures is around about 1,000,000 degrees Celsius, or 4 significant figures. Anyway, so this effect of fusion causes a release of energy, which increases the temperature. So you can start fusion at 1,000,000 Kelvin, 1,000,000 degrees Celsius, near enough. But because it produces energy, yes, it does create energy. Because it creates energy, that will actually have the effect of increasing the temperature even further. We're trying to do this sort of reaction ourselves here on Earth. We're trying to do it to make nuclear fusion a viable power source, a way of generating electricity for us. So this sort of reaction releases, it says here just, which is a clue that it's not really a lot. It says just 0.9 mega electron volts per reacting ion. Mega electron volts is just a unit of energy. It's not like the joule. It's a much smaller unit than the joule. 1.6 times 10 to the negative 19 joules. So just think about that. 1.6 times 10 to the negative 19. That's 0.000000000000000000000. I've lost count. Some zeros. 16 joules. That's not a lot. Is 1 electron volt. So that gives you an idea. It's a more convenient unit to use for energy. Mega electron volts is millions of electron volts. So that's not actually very much. You can get much more if you can do fusion like this. So here, what you've got is hydrogen fusing with hydrogen. Not deuterium with deuterium, which is a heavier isotope of, you see, I just said heavier, when I should have said more massive. This is the sort of clumsy language I'm talking about. Anyway, a more massive isotope of hydrogen, like deuterium, it turns out it's actually easier to fuse. You need hundreds of millions of Kelvin, hundreds of millions of degrees Celsius, 10 to the 8 Kelvin, in order to get hydrogen, that's just 2 protons, to fuse together. Much higher temperatures. But you get much more energy out, which means the heating effect is far greater. Yeah, you're getting 4.4 mega electron volts per reacting ion. And we know this because we've done experiments. We know this stuff. You need a higher temperature to get this sort of fusion to happen. But when it happens, it releases more energy. So, proton-proton fusion chains. The one I showed you just now was one example. Here are some others. So the one I showed you before, we had proton, 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 proton. So in total we had 6 protons coming in, and we had helium coming out and 2 protons coming out. So 2 of the protons through this process turned into neutrons. Fine, okay. So what's going on here then? Well, here we have 3 protons coming in and a helium. So we've got proton, proton, proton going into this reaction. These 2 protons combine to form deuterium, but then that deuterium fuses with another proton to form this isotope of helium, helium-3, which interacts with helium-4 to produce this thing here. This thing here, which you can see has got 4 protons and 3 neutrons, so that is beryllium-7. Now we know that this happens in stars because we've found evidence of beryllium in stars. That beryllium will decay into lithium, and there's a particle missing here. There should actually be a positron coming off here, which isn't drawn. So we know that. I wonder why that positron's not been drawn. That's a mistake on this. But there should be a positron here. And we know that there is lithium-7 in stars because we've seen the evidence for that as well. Or we can have the proton-proton 3 chain, which is the one on the right, and this has got boron in it as well. And we know that this happens in stars because we've seen boron as well in stars. So all 3 of these types of reactions can happen, but they happen at different rates and they happen at different temperatures. So we can look at the proportion of the star that contains beryllium or boron and use that to determine things like the temperature of the core of the star. It's very clever stuff we can do. And I don't have the details on that, but I'll leave it there. We also have things like triple alpha fusion. And you can see the diagram here. We get 2 alphas fusing if they're moving at a high enough temperature, moving fast enough, so they need to be at a high enough temperature. Again, we're in the order of tens of millions of Kelvin. And you also have to have plenty of helium for there to be enough helium around colliding for this to happen. So this is going to happen with older stars, and that's why it says here it happens in some red giant stars. They're older in the life cycle, so you see more of this happening. And this forms carbon. So the more carbon you see in the star, the more you know that it's been operating at a high temperature and it's getting on a bit because it's got enough helium to form that carbon. Now, once you've got the carbon, we can have some interesting interactions like this. CNO cycles. So here, carbon will turn into nitrogen, which will turn into carbon, which will turn into nitrogen, which will turn into oxygen, which will turn back into nitrogen, which will turn back into carbon. Nitrogen, carbon, nitrogen, oxygen, nitrogen, carbon, nitrogen, carbon, nitrogen, oxygen, nitrogen, carbon. They're different isotopes. Well, most of the time they're different isotopes. And this cycle, it's almost like a catalyst, if I was a chemist, is what I might call it. It takes your hydrogens in and it turns them into helium. So if you have a look, in total we have 1 hydrogen coming in, 2, 3, 4 hydrogen coming in, and out comes 1 helium. Now for this to happen, you've got to have that carbon, which is then going to turn to nitrogen, which is then going to turn to blah, 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 blah. Now, it turns out that this only happens in the more massive stars, but it's the most dominant in stars around 1.3 times the mass of the sun. That's interesting. It releases loads of energy each cycle. Loads of energy. But if you look, it starts at temperatures of about 15 million Kelvin, and about 17 million Kelvin is the one where it becomes, so not 100 million, but around those sorts of temperatures is where it becomes the most significant fusion reaction. Okay, so what happens next? Well, I've got a graph. I just thought I'd include this to show the dominant fusion process. On the x-axis, we've got something to do with temperature. That's what that's supposed to be showing. On the y-axis, you've got the sort of relative energy output, the amount of energy we're getting out. They're logarithmic scales, numbers on the scales, so it's not a linear graph, but don't worry too much about that. Here's the sun. So we do get a bit of CNO, it's just not the dominant one right now. Proton-proton chains, all 3 of those are more dominant for us. Higher temperature stars can have more of the triple alpha, which I think we already mentioned. That was around hundreds of millions of Kelvin. Right. Interesting. Now, the spec mentions several times basically the same thing. One of the things it mentions is understanding what the forces are doing at different stages in the sun, in particular the sun's life cycle. Don't like calling it a life cycle. So I've just put them in this table here, and you can read that yourself. I don't want to go through every detail on this table. You can always pause the video and read it yourself. But this is what's going on inside stars. These different forces that are acting, and that's causing the effect on radiation pressure and the overall effect on the star. White dwarf and black dwarfs, there's almost no radiation pressure because nuclear fusion stopped. There's no nuclear fusion anymore. So the effect of that is that they continue to emit light as they cool until they're cold, and then they emit nothing. So I'm not going to go into all of this detail about each of these stages. You can read that yourself. Let's move on to the next bit. I included this slide because I thought this was actually really interesting. What you're looking at here is the periodic table of the elements, but where the elements came from, coloured in, well, the proportion of the block for that element is coloured, showing the proportion of where that element came from. So you can see after the Big Bang, actually it suggests there was some lithium formed just from the Big Bang, from that process. So hydrogen, helium, some helium formed from dying low mass stars, some from exploding massive stars, and so on and so on. What really interested me was that we often learn that you need to have supernovae to fuse higher than iron, which makes sense, I suppose. And yet we've got things like exploding white dwarf stars being the main way that we get these elements higher than iron in the periodic table. And if you want to get right up towards things like, lead, uranium, right up this end, actually you need to have neutron stars merging. Now that is going to produce some sort of supernova, sure. It's going to be a hell of a supernova. It's enormous. So I just thought that was interesting. That it's just a hint that there's a lot more interesting physics that we don't do in GCSE physics, or even at A-level physics, that astronomy, if you study that at university, will teach you. I think it also shows quite nicely how astronomy goes from just learning the names of planets and stars to doing real physics, which is quite exciting. Now, speaking of real physics, we're going to talk about electron degeneracy. Because if we've got stars that are collapsing, how far can they collapse? So we know there's a radiation pressure which is going to increase as the matter of the star gets closer together as it collapses. That's fine. But what if there's so much mass, so there's so much weight of material that we can collapse down even further? Well, there's a limit to how far we can collapse. So electrons have a property called spin. They have mass, yes, they have charge, yes, they also have spin. Now, do not confuse spin with what this top picture shows, this spinning ball. We're talking about quantum spin. It's an entirely different thing. It's related to the magnetic moment, the magnetic field around electrons. It's quantized into just two values. There's only two values of spin that electrons can have. The reason why we can't visualize it like this is because electrons aren't balls. We can either consider them to be points, or their position can be given by a probability distribution function. It's a lot more complicated. So I'm afraid we can't use some classical physics ideas like spinning tops. But it's still a useful analogy, which is why that's the language we use. Now, you can only put electrons together if they have unique sets of quantum numbers. And the quantum numbers are things like charge. Well, they all have charge of -1, so that's not going to be unique. But there's also things like the principal quantum number. That's the energy level that the electron sits in. You've also got angular momentum. We're not ready for that yet, but we've also got spin. So let's take this simple atom here. This one's lithium. We've got two electrons, and they're orbiting this nucleus, and a third electron. Now, why can't the third electron go into that first shell, that shell that's closer to the nucleus? Well, because there are already two electrons in there, and as electrons can only have one of two spin states, we can only put two electrons in there. We've got one we call spin up and one we call a spin down, and that's it. Now, they are unique electrons. Okay, they have the same principal quantum number. They're in the first shell. And okay, they have the same angular momentum quantum number, which for both of these is actually 0. But they have unique spins. One is a spin up, call it +1/2 for technical reasons. One's a spin down, call it -1/2 for technical reasons. Which means a third electron can't sit in that shell. It just can't. The universe won't let it. Now, this does something interesting. This means that if we start trying to push atoms together enough, the electrons can't get too close together. Because if you try and put the electrons too close together, the universe won't let them. They cannot be pushed closer together. that's not how fermions work, and fermions are the names of particles that behave like this. I don't think I've put that on these notes. Doesn't matter. So the Pauli exclusion principle describes how fermions, this type of particle, the electrons are fermions, so are protons actually, so are neutrons. You can't push them too close together. They just won't go. So the whole atom is in the lowest energy level it can be, even though this electron is actually in a higher energy level, because you can't push them any closer together. So I've talked about bound electrons here having the principal quantum number. So the principal quantum number for this electron is 1, for this electron is 1, for this electron it's 2. And the third shell it would be 3, and the fourth shell it would be 4, and so on. And there's some other quantum numbers I've mentioned. But basically, the electrons, if it's a cold temperature gas or something, the electrons are going to sit in the lowest energy state they can. But even in a star, those rules still hold. You can't push the electrons and the protons and the neutrons together. They won't go. And that produces something we call electron degeneracy pressure, an outward force just because the atoms will not get closer together because the electrons can't occupy that same place. They're not allowed to. These two electrons can. But that's it. Any more electrons, they can't occupy that same space. So I've got a little bit of nonsense here for you to read if you want to. It says matter outside pushes in, matter inside pushes out. That's Newton's third law. So the matter inside gets denser and denser and denser, but it's got a limit to how dense it can get. Barycenter, by the way, just means the center of mass of a system, where we can consider the mass of all the system to be on average. So these get closer together, but there's a limit. They can't get infinitely close together. If we try to get them infinitely close together, that force, that mysterious force caused by electron degeneracy prevents them from touching, which is what I've described it as here. So what's going on in white dwarfs then? Because white dwarfs they're not having nuclear fusion going on. They're getting colder and colder, and eventually they're going to be black dwarfs, which means they're so cold that they no longer consist of a plasma. They're too cold to be called a plasma. So what's happening there? Because we can't just have matter get closer and closer and compress. Well, that's what gives us an idea of the size that white dwarfs can collapse down to, is this electron degeneracy. This force that prevents the unchecked gravitational compression of white dwarf stars. It's what prevents them from getting too small. So just a summary about when do we get our white dwarfs? Well, we can get white dwarfs with lower mass stars. They're still pretty massive. I mean, come on, they're still stars, but they're lower mass stars. What do we have happening? Well, you get accretion of mass forming a protostar. That protostar then turns into a main sequence star when nuclear fusion becomes stable. That main sequence star is when we've got those two forces, the radiation force, radiation pressure, and the gravitational force. They balance. The radiation force is going to reduce because of the using up of the fuel, so the outer layers are going to escape as the middle bit compresses down. The middle bit compresses down, increasing temperature, which pushes the outer layers out. The outer layers continue to puff out, and the bit that's left in the middle is still going to be heavy. It's still going to be compressing down, but it's a limit to how far it can go, and it ends up being a white dwarf. Anything a higher mass, something more interesting happens. You get more massive than the sun. It's more than about 1.4 solar masses, then it won't turn into a white dwarf. Now you'll notice that the first bunch of stages here are the same. The outer layers this time, however, don't escape. There's so much mass that although they puff out, they fall back again. And as they fall back, they get faster and faster and faster as they fall, because that's what happens when things fall. They get faster and faster, accelerated by the force of gravity, compressing down, collapsing down. And it's like I mean, we can reproduce these sorts of reactions on Earth in particle accelerators by accelerating protons towards each other sufficiently fast. That's what's happening with the mass of this star. So we get huge high-energy collisions between with lots and lots of matter as these things contract down, and it will cause a supernova. Now, how do we get this 1.4 solar mass limit? How do we get that? It's called the Chandrasekhar limit. It's, as we say, 1.4 solar masses. If you're below the Chandrasekhar limit, so you're less than 1.4 solar masses, then the gravitational force is never going to be bigger than the electron degeneracy force. Now, I said you cannot get electrons into the same quantum state. That is true, but they don't have to stay electrons. Electrons can combine with the nucleus. You know, they don't have to stay electrons. So above this limit, higher energy particle physics happens to get rid of the electrons, to get rid of that problem. So that's what happens. The degeneracy force now is not big enough. So now the electrons are forced to push close enough to nuclei that they will actually be, or to any protons, that they'll actually be absorbed by those protons. Something called electron capture. So we're getting rid of the protons because we're absorbing the electrons into them. What we're left with is neutrons. And that's how neutron stars can form. This has been theoretically graphed, and I'm not going to go into too much detail about this graph. Non-relativistic Fermi gas, okay, well, we know what a gas is. Fermi means it consists of fermions, so we're limiting the fact that these particles can't be in the same quantum state. Non-relativistic means everything's moving slowly. Actually, that's not how it's going to work. Everything's going to be moving fast because we're contracting down stars. So when we start looking at things moving fast, we can't use non-relativistic physics. That's the physics that we know, speed equals distance over time and other such myths. That's not going to work at high energy physics, at those higher speeds. We need relativity. We need Einstein to save us. And when we employ relativistic physics, people cleverer than me have plotted a graph of what that looks like, and we get this limit here, this Chandrasekhar limit right here, where the minimum size that you can reach is down to 0. And then actually there's nothing beyond that. We can't. That doesn't exist. It's never land. We can't form these bodies with electrons smaller, or because there is no one small. We've reached 0. There is nothing smaller, but with more mass. We just can't do it. We've already reached 0 size. We can't do it. It's impossible. It doesn't work that way. Syntax error. So what happens? Well, in that case, we have the opposite process to what we had with that beta decay. In beta decay, we get a neutron turning into a proton by emitting an electron. Here we've got a proton turned into a neutron by absorbing an electron. Now I've got these two different what we call Feynman diagrams here to show that it can happen with the emission of a W plus boson from the proton or the emission of a W minus boson from the electron. In fact, they both happen simultaneously with different probabilities. I don't think you're ready for that sort of quantum physics just yet, but you will be. So if we get high enough gravitational force because there's enough matter, then these electrons are going to get so close to the protons. Remember that they are all pushing against each other because of degeneracy as well. So when these electrons get close enough to the protons, they will be absorbed into the protons. They will be captured by the protons, leaving behind neutrons and neutrinos, but they very weakly interact. So what we're left with is just a core of neutrons, and that's what we can call a neutron star. Now, around the outside of the neutron star's core, you're going to still have nuclear fusion, you're still going to have all the other stuff that you get with stars, but the core of it becomes just, neutronium, I guess. It just becomes neutrons, a cluster of neutrons, as those electrons get captured. So what about if I've got even more mass than that? Can we collapse down even further? Well, inside our protons, not protons, we're talking about neutrons. Inside our neutrons, we have quarks, and there's three quarks in particular we're interested in, which we call the valence quarks. There will be other quarks as well that come into and out of existence all the time. Protons and neutrons are weird things. But let's just deal with the valence quarks, these quarks that we use to identify the nature of this particular composite particle, this thing we call a baryon. Again, I'm using a lot of words here. If I'm using the words quickly and skipping over them, that's an indication that perhaps you don't need to know it quite at this stage, but it's also an invitation for you, if you're interested, to search for things like baryons and work out what they are. It's not required for your astronomy GCSE, though. But I do think you should know that there are these things called quarks inside protons and neutrons. I do think you should know that they obey the same Pauli exclusion principle that electrons obey. So here we've got two down quarks, but they do have different color charges. So we're talking about quantum chromodynamics. So they're not limited. They can be as close together as they want to be, these three quarks inside the proton. Of course, there are other quarks inside this proton and antiquarks. Well, this is a neutron. So there are quarks and antiquarks inside this neutron as well, but these three valence quarks are what we're focusing on. If I have another neutron coming near to it, is there a limit to how close together they can get? Well, they're both neutrons, so they're both neutrally charged. So there's no repulsion, electrostatic repulsion, as there was with protons. So I took off the electrostatic repulsion part of this graph we saw earlier, but we still have strong nuclear repulsion at these short ranges of about 0.8 of a femtometer. So these quarks from neighbouring protons can't get any closer together, so we can't collapse down the neutrons any further. Well, that is unless the gravitational force is bigger than that repulsive force from the quarks. And if the gravitational force is even bigger than that, in other words, we've got even more mass than that, then the neutron star is going to compress down even further into a black hole. Now, in the spec, it talks about neutron pressure, about the fact you can't push these neutrons closer together. It's to do with quark degeneracy. Really, that's what it's to do with. It's similar to electron degeneracy. It's also to do with the fact the strong nuclear force is repulsive. I mean, that's all part of the same thing. Are they different forces? I'll leave that for you to figure out later, or Google, or study it at university level, because that's the level we're talking about here. But if you've got a nice stable equilibrium between that outward force from the neutrons not being able to be any closer together and the inward force from gravity, then you've got your neutron star. But if there's even more mass, so there's even more gravity, then that will cause your neutron star to collapse down even further. So balancing stars, balancing forces, balancing pressures. Main sequence star, we can't push the ions together any closer because of the radiation pressure. It balances with the gravity. White dwarf star, we can't push the atoms any closer together because there's no radiation pressure, but there is electron pressure, electron degeneracy pressure, which balances from the gravity. Then we've got the neutron stars. They can't be pushed any closer together, even though there's no electron degeneracy pressure anymore, because there's no electrons or neutrons. They can't be pushed together any closer anymore because of the neutron pressure, the neutron degeneracy. But then black holes, the gravitational force is so strong that then even that neutron degeneracy and even that neutron pressure can't stop that collapse, and they will collapse down to a volume of 0. Or they'll converge towards a volume of 0. So that's everything you need to know about stars, I guess. Now, the spec talks about nebulae, and for no reason I can understand, it says, you should know the types of nebulae, which you've done before, but for completeness, we've got two types of nebulae: absorption nebulae and emission nebulae. An emission nebula is one that emits light. An absorption nebula is one that, you guessed it, absorbs light. So absorption nebula will have lots of dust. It's not very dense, necessarily. It's not going to be dense enough for it to be glowing. So it's going to have lots of dust in there, and it's going to absorb any light from the stars behind, so it looks like, you can see this picture, a dark, wispy cloud. The emission nebula, that's going to be either a bit more dense, or it could be hydrogen that's being excited by nearby stars and made to glow. Stars are emitting radiation, and if your nebula absorbs that radiation, then it can glow. It can get excited. The atoms can get excited and glow, and that will give you an emission nebula. Sorry. No idea why the spec had that bit randomly chucked in, but hey ho, let's carry on. We've got, it's very odd. So now we've got how long do stars last. You have to have an appreciation for this, for the lifetime of stars. Something like our star, about 10 billion years. And then you can see the scale here. I'm not going to go through all this. I don't think I need to. The table says everything that needs to be said. Time scales here. The A means years, from the same thing as annual. It means years. So MA is millions of years, GA is billions of years, KA is thousands of years. That's what that means. So emission and absorption nebulae can last for around about 50 million years if they're about the same as a solar mass, and about the same if they're much greater than a solar mass. You're not going to get black dwarfs at masses much greater than solar mass. You get more than 1.4 solar mass, you can't make your white dwarfs. So that's why that's not included on the right-hand side. Instead, we've got supernovae, and they last for less than a year, just for hundreds of days, some of them even shorter than that. Then you've got your neutron stars. They'll just sit there forever, as far as we know, or long enough that there's no point measuring it. And black holes are the same. Okay, fine. The specification now talks about black holes in a bit more detail. So the detection of black holes. How can we detect them? We can detect them. Black holes were first theorized by Albert Einstein as a solution to general relativity, to one of his general relativity, a solution to general relativity. Let's leave it at that. It turns out that we could detect them, but not for decades, not until decades after they were first proposed. So how do we detect them? We can use things like this. So LIGO, light interferometry of gravitational waves. LIGO works like this. You've got this huge structure here, and you can see the two arms here. There's mirrors at the end of them. You shine a light, bounces off the mirror, bounce back, and then you combine it again. That's the light source here, sorry. So bounce off the mirror, comes back, and then bounces like this. Have we got the light sources the right way around? I'm not sure. And there's another mirror on the other arm. And when the light comes back together, yes, this is the light source here. It goes along there, bounces back, bounces off the mirror, or bounces off the mirror here and then comes back. So this is a partially reflecting mirror. If the light arrives and it's what we call in phase, and a picture speaks 1,000 words, so you see what I mean by that. The waves arrive together, then we see plenty of light. But if they arrive and they're not together, so in other words, this mirror has moved, perhaps, then we're going to get the waves no longer arriving together. They're going to interfere destructively. So the waves are going to do this, and that's going to cancel out. So if there's a gravitational wave, then we should expect to see, at the same frequency as the gravitational wave, we should be able to see the light basically flashing. And that would happen because the arm of the interferometer, one of these arms, is being made to contract and expand. Now, why would gravity do that? Well, because gravity in general relativity is to do with curvature of space-time. And so if we've got a gravity wave, then we've got an oscillating curvature of space-time, changing the relative dimensions of space-time as that wave passes through. So by putting the two arms at 90 degrees to each other, if the wave comes through in a certain direction, causing, as this one shows here, some sort of gravitational anomaly, causing some sort of contraction or expansion of space-time along here, we'll be able to detect it. And we did. That's the exciting thing. We detected the gravity wave that's produced when two neutron stars merge. What did theory say? What did we detect? And they matched. That's really good physics. What was formed at the end would have been a black hole. We can also see the effects of them. Not quite like this artist picture on the left. That's a simulation of what it would look like if we were centered on a view on a black hole with the galaxy sweeping behind it. Of course, it'd probably be the other way around. That's funny things how parallax works. But we have seen the examples of gravitational lensing. This one, I think it's called Einstein's cross actually, but I might have got the wrong one. This one, can you see there's 4 stars and there's a thing in the middle? Well, the thing in the middle is actually there's a black hole right in the middle of it. It's actually a galaxy, but there's a black hole right in the middle of it. These 4 stars, I believe, are actually galaxies, but they're the same galaxy. And we can tell they're the same galaxy because we can look at the light from them and see that it's identical. These are the same galaxy. We just see it 4 times. And we can see things like this. We see the galaxy, but it's actually smeared out. And these 3, they're the same galaxy smeared out because of the effect of having a black hole between that galaxy and us, causing light to be bent around that galaxy. Yeah, light is attracted to black holes. Attracted to them because the space through which the light passes is curved. That's what gravity does. So that's pretty exciting. We saw plenty of pictures like this that confirmed the existence of black holes. We also did some astrometry. That's very precise measuring of the positions of stars. We did some astrometry. Here we go. We looked at these. There's an interesting thing about this. This is recorded over the course of 20 years. And as you record over the course of 20 years, technology improves. So all the stars start all blurry, and then they get clearer. Well, that's because we're getting better and better at getting pictures of them with better equipment and better technology and so on and so on. So, I think that's quite nice to see, actually. But it looks like there's something around here-ish that seems to be attracting all these stars. Well, let's have a look at it. There it is. Look, we can see it from this graph here. We've tracked the trajectory, extended it. Kepler's laws, if you remember, all orbits are elliptical, so we continued those ellipses, and they all correspond to there being a barycenter, a focus of the ellipse right here. So that is, there should be some really massive star there, and yet there's no light coming from there. So that indicates that perhaps there isn't a star there. Now, what we're looking at here is a very small region right in the central bulge of our galaxy. That's what we're looking at here. So, we're looking at such a small patch of sky. And you can't do this on Earth because there's far too much atmospheric interference and all the rest of it. But there you go. There you go. That's pretty good evidence of black holes. Still not convinced. So you've seen gravitational waves we've detected that match theory. That worked. What else have we seen? We've seen gravitational lensing as predicted by Einstein, which can only happen with the masses we're talking about with black holes. That hasn't convinced you. So we've done some astrometry. That's still not convinced you. Fine, we'll take a photo of one. Bang, there it is. This is incredible. This is quite new, actually. It's only, relatively new, we should say. It's only a few years, really. But these are radio telescopes taking terabytes, petabytes of data and combining them to see what it looks like. Now, there's an interesting question is why does it look dark in the middle and light round the edge? But if you look at images, photographs even, through a telescope of the sun, you'll see it looks brighter around the edge and dimmer in the middle. And that's just because there's more matter when you're looking at it at the edge than there is in the middle bit. Imagine a balloon that you inflate, and there's more rubber you're seeing here than here. So that's why that happens. We didn't just happen to get lucky and there's a black hole, which is a lovely hole perfectly orientated facing us. It's not quite that. There will be obviously a lot of radiation coming from the whole region around the black hole, but we've had to dial down the contrast so that we can actually visualize where it is, and that's what we see. That is they're 2 different photographs. Photograph in quotes because it's not using light, radio photographs of black holes. Now you should be fully convinced. And that is everything that we needed to cover for this topic on stellar evolution. That was a big video. How long? Woof, nearly an hour and a half. But I'm hoping that was useful. I have prepared the presentation for topic 15 as well, so I'll record that hopefully a little bit quicker than I have been doing and get that out to you as well. If you found this video useful, then do subscribe. It's important so that you get those notifications. There's also a Discord server, and it's not very active at the moment for astronomy because it's only recently set up, but if you can get on there, you can ask some questions. There's a Q&A forum within that Discord server, and there will be a chat thing so you can talk about astronomy, ask questions with each other. How do you find the exams, that sort of thing. Where can you find resources, as long as they are not under copyright, because I'm not going to have my Discord server shut down, please. But there'll be a link to that below. If you click somewhere below in this video, you'll see a link to that Discord server. Go ahead and join that. Let me know who you are. Let me know what you want to do: GCSE, physics, astronomy, whatever, and I'll get you added to the right role. And last thing, I've been thinking about whether or not to do tuition sessions for GCSE astronomy. There's been a few requests for it, but I'm reluctant. And the reason why I'm reluctant is mainly because of time. So I'd have to have quite a few people that want to do it, and I'd have to have quite a bit of commitment from them. I wouldn't want to be sat there twiddling my thumbs and no one coming along to the tuition sessions. So if there was a lot of interest, let me know. Again, you can let me know in the comments, or you can get on that Discord server and let me know. If that's something you think would be interesting, I can set something up. Also, check out my physics tuition. If you're GCSE, or even if you're an A-level physics student, check out my GCSE and A-level physics tuition. It runs every week, usually on Thursdays, not during holidays, but every week on Thursdays. You can go to physicswithkeith.com, have a look at what is on offer. No one wants to listen to me talking any longer. So thank you so much for getting to the end of the video. If you did, if you didn't, you're not going to get this message. Stay safe, and I'll see you in the next video.